Greetings and welcome to Distillate. In the previous lecture, we started solving a very interesting problem where we had this kind of a chemical reaction. This was a constant volume reaction, and we said that its rate is given as this. So it is the rate depends on the concentrations of A and B, and it is nth order with respect to A and mth order with respect to B, with K being its rate constant, right? We had data in this form. We had time, we had concentrations of all the species A, B, C, and D with respect to time. So maybe we could remember the structure of the data. So we have time intervals of 0.1, and we have this data till time 2, right? So that's the data that we have with us, right? So in the previous lecture, we started by reading this data into our Python script, and now we'll try to do some cool things with that data in order to evaluate the rate constant and the orders, right? So if you remember, we had discussed about linear regression, and we could do all of these things. We could find these constants using linear regression. But before we go there, there's one thing that we have is the rate of the reaction. So over here, so far the data that we have is not really the rate of the reaction. It is just concentration versus time, right? It's a concentration versus time array given to us basically, and we need to find out what the rate of the reaction is at different time points, or more importantly at different concentrations. That is what we are willing to find out right now, right? So let's try to understand how would we do that. So since we know that the rate of the reaction is nothing but minus dca by dt, right? So this is for a constant volume reaction. In general, the rate is given as 1 over V, the number of moles by dt. But since the volume is constant, we can send it inside the derivative and we get this minus dCA by dt, right? So this implies we need to find the derivatives of concentration with respect to time rather than concentrate the concentrations and times themselves, right? So that is what we need to do. So now let's try to figure out how we would do that. So this definitely involves differentiation, and what we'll be doing now is going to be numerical differentiation. So in these lectures, we'll also be touching a few concepts from numerical mathematics, because definitely a lot of chemical engineering involves solving differential equations, taking derivatives, finding integrals, and so on. And for that, to do that using Python, you will definitely need numerical math. So this is the first entry in that, which is numerical differentiation. So let's try to understand how can we numerically evaluate derivatives of a particular function using numerically, basically, right? So let's try to evaluate derivatives numerically. So when I say numerically, what do I mean by that? So numerically means just using either addition, subtraction, multiplication, or division. It's only these operations, or of course your other exponents, sinusoids, etc. But basically, I want to carry out only these operations in order to solve any problem. So for example, let's take the example of differentiation. So in case of differentiation, let's say if we have to find the derivative of function f, let's say df by dx, right? Now we can do this analytically. If you have a complex function, we could use, say, product rule and so on and so forth. We could do use simple formulas, whatever we know. But the computer cannot do this calculation analytically, right? So it would always want to do something numerically. And when it tries to do something numerically, it definitely uses addition, subtraction, multiplication, or division, right? These operations are what a computer uses. So in most of the numerical math, you will see that all the complex mathematical calculations that you do, whether it is taking a derivative, whether it is taking an evaluating an integral, whether it is solving an ordinary differential equation or a partial differential equation, all you do in all of these cases is break it down into these operations: addition, subtraction, multiplication, and division, right? You make matrices at times, and that also is just, if you, let's say, do matrix multiplication, that is once again just addition and multiplication. If you perform, say, inverse of a matrix, that is once again multiplication, division, and so on, right? So altogether, it's only these operations that you can perform in a computer. So all the numerical math that has been developed, it has been done so that you can represent any complex mathematical calculation into addition, subtraction, multiplication, or division. That's what we are going to do. So let's see how exactly we could do this for a derivative. So one thing that we can very easily use for most of the numerical maths that we do is known as Taylor series. So when we talk about a Taylor series expansion, we could we could expand, let's say, fx plus h being a very small change from x around x, right? So when we do that, that is going to be fx plus f dash x into h plus f double dash x h squared by 2 factorial plus f triple dash x h cubed by 3 factorial, and so on, right? Or basically it's summation of f n x, f n x implies the nth derivative, times h to the power n over n factorial from n equals to 0 to infinity. That's the Taylor series expansion, right? So over here, you see that we have got the first derivative, right? So if we just simplify this and write it as fx plus f dash x h plus all the other terms of order h squared, right? So if we do something of this kind, and we say that, let's say, h is very, very small, so we can neglect all of these terms. So we'll neglect all the terms of order h squared. And from this simple simplification, you get f dash x equals to f x plus h minus fx upon h, right? So this is how you numerically evaluate a derivative, right? This is how you numerically evaluate a derivative. Now, over here, you see one thing, that if we have, let's say, a data point xi, right? So in order to calculate the derivative at this data point xi, what we need to do is we need to find some data point, which is, let's say, delta x further, like delta x in front of this xi, right? And then we use this formula to get the derivative at xi, which is f xi plus delta x, h being the step size over here, so delta x minus f xi over delta x, right? We've written the same formula, we've replaced h by delta x, right? So that's how you can find the derivative, right? Now, since we are using 2 points over here, one is xi and one is xi plus delta x, the 2 points are such that the derivative that we are evaluating is at a point, uh, at a given point, and the 2 points are the point itself and a point ahead of it or forward of it. So therefore, this kind of a formula or this kind of a differentiation calculation is known as a forward difference formula or a forward difference method for evaluating the numerical derivative. You can similarly do for a backward difference where you replace delta x by minus delta x in the above expansion. And once again, you will be able to get f dash xi equal to fxi minus fxi minus delta x over delta x. So in this case, you see, you've used the point and another point which is backward from the given point. So therefore, this is known as a backward difference method. Right. And similarly, if you so you perform the same Taylor series expansion, just in place of plus h, you write minus h. So you'll get terms of fx minus h. And if you subtract the two, right? If you subtract the two, so I would leave it to you as an exercise to derive this kind of a formula. But if you subtract the two and then evaluate the derivative, you will get that f dash xi in this case would be fxi plus delta x minus fxi minus delta x over 2 delta x, right? And therefore, if you see the point where we evaluate the derivative uses points ahead and behind it. So basically, the point is at the center. So this is known as a center difference formula or a central difference formula. Right. So this is known as a central difference or a central difference method. Right. And one thing that you will see over here is that when we performed this calculation, we neglected all the terms of order h squared. Similarly, in the backward difference method as well, we would neglect the terms of order h squared. But in when we subtract fx plus h and fx minus h, the terms with even powers of h get cancelled off because their sign never really gets changed, right? So you will just have f dash xh plus f triple dash xh cubed and so on. So basically the first term that we neglect in this calculation has order h cubed, right? So the first term that we neglect in this has order h cubed, and because of that, this formula is generally more accurate. Right. So as long as your h is small enough or your delta x in this case is small enough, you can use either of the three formulas, but it is usually advisable to use the central difference formula for most of your calculations, right? So that is what we'll be doing as well, right? And similarly, just like we have calculated the first derivatives, we can similarly use Taylor series expansions and do some mathematical manipulations here and there to evaluate second derivatives, which we'll not be discussing that in this video, but certainly we'll have to use second derivatives somewhere or the other in further lectures. So we'll talk about second derivatives then. But this is how we calculate the first derivatives. I would highly recommend you to understand how these formulas are derived and maybe try to derive a formula for second derivative as well and see whether it is accurate, more accurate or less accurate compared to the backward difference, forward difference method and so on. right? So you could try multiple things. But let's get back to our problem right now. So what we have is uh, the data for time and concentrations, right? That's the data that we have with us, right? And we have, so basically, if we have to evaluate, say, dca by dt at a given point I, so we'll do that. Let's say we are using the central difference formula. So we'll say that's equal to cai plus 1, which is the point ahead of it, minus cai minus 1, the point behind it, upon delta t. Sorry, 2 delta t, right? So since we know our uh, time is 0, 0.1, and so on, so delta t for our problem is 0.1, right? Now, in order to evaluate the derivative at time t equals to 0, we would need, let's say if we are using the central difference formula, so we would need a point behind this. So we'll need a point at minus 0.1, but we don't really have that, right? So therefore, when you have to evaluate a point at the boundary, so like over here, this is the boundary of time. So if you have to evaluate a point at the boundary, people do two things. One is that they either consider a fictitious point, a hypothetical point, and then do this calculation. But that we cannot really perform right now, because we do that when there's a boundary condition. We'll talk about that later on when we deal with ordinary differential equations. But we cannot do that right now. So the only other option that we have is to use the points that are available, right? So we have this point and we have the point next to it. So for this, the evaluation of derivative at the at time t equals to 0, we are going to use forward difference, right? We are going to use forward difference, right? For all the others, we could use the central difference method because we have a point behind it and a point ahead of it, right? And finally, at the last point, which went on till 2, if you remember, we have a point behind it, right? So here we would use the backward difference, right? So in the first point, t equals to 0, we are going to use the forward difference. For the last point, we'll use a backward difference. And for all the others, we'll use a central difference formula, right? So hopefully this part is clear. So now let's go on to code this thing in our Python, right? So in the previous lecture, we had read the concentrations. So let me just run this maybe, and we can see that we've read time as an array. We've read concentrations as an array, right? Now let's get delta t or dt. So dt over here, I'll just write this over here. This is numerical differentiation, right? So dt over here is nothing but the time, let's say the first entry of time minus the 0th entry of time. And since the grid is uniformly spaced, so all of the t1 minus t0 is equal to t2 minus t1 and so on and so forth, right? So this is the time difference over here, right? Now let's calculate the derivatives. So remember, derivatives have to be stored in an array, right? So let's try to do that. So this array is going to be RA, which is dCA over dt, right? And at the first point, which is at time t equals to 0, we'll use the point next to it, CAI plus 1 minus CAI. So let's do that. So that's going to be CA I plus 1. So it's the first point. So CA1 minus CA0. and the entire thing divided by dt, right? One thing that may be useful is that when any programming language has to perform division, that takes a lot more time and it's a lot more complex where compared to multiplication. So since we've seen that in every derivative we have to divide by dt or 2 dt, it is a good idea to use another variable such as dt inverse as 1 over dt. So what this does is this has to perform the division operation only once, and then you could multiply dt inverse everywhere. So it has to perform lesser number of division operations. So your code will be a lot more efficient, right? So this is the first entry of the rate array, right? Then the next entry, we could use either list comprehensions or maybe let's start with a for loop. So for I in range, um, so we have to start with 1 now because we've already gone over 0, right? So for I in range 1 comma, and we have to leave the last point. So length of time minus 1. So this takes all the points in between the first and the last point, right? So ra dot append, right? And ca I plus 1 minus ca I minus 1. This is central difference into 0 0.5. 0 0.5 because we are dividing by 2 times dt inverse. So once again, we have reduced the number of division operations and we have increased multiplication operations, right? So that's for all the other points at the center. And finally, the last is going to be the last point. So let's CA. Now here we use backward difference. So CA length T or the last point. So CA minus 1. That gives you the last point, right? Minus CA second last point. So you could say minus 2, right? Into dt inverse. So this is once again a backward difference operation. You could also write this as length t minus 1, and this could be length t minus 2. It's the same thing, right? So we've evaluated the rates, and if we evaluate this, we'll see the rates as this. And now you see this has been evaluated as a list, so we can convert it into an array. So array equals to np dot array the list, which is r, right? So now it has been converted into arrays. And now you see this is the rate. The rate is definitely negative because a is actually decreasing over time. And therefore we use minus RA to represent the different rate of reduction of A, right? Or rate of disappearance of A. So that's a better way to represent the rate. So if I would want to call this as rate of disappearance of A, so I'll just multiply it by minus 1. So that's equivalent to your minus RA, right? That is equivalent to minus RA, right? So that is what we have done. So over here, the first thing that we've done is evaluating the first point, the derivative at t equals to 0 using forward difference. All the other points, we used central difference. And the last point, we used backward difference. In most cases, you will be doing the same thing. You will be evaluating derivatives in this way: forward, central, and backward. So now we have rates. Now, the next step is going to be to calculate or to evaluate the constants n, m, and k. So in the next video, we'll see how would we get these constants.